Welcome to this lesson on speed and energy brought to you by STEMpathize for grades 5 through 6. So here's some information about us. We are a group of high school volunteers from STEMpathize. STEMpathize is an organization that hosts hands-on workshops for students like yourself to gain interest in STEM subjects. So science, technology, engineering, and math. Our website, seen down below, stempathize.org. Instagram, same thing, stempathize.us. YouTube, STEMpathize. So here's an icebreaker or some information necessarily about me. My name is Kyle. I am a rising 12th grader, so senior in high school. And my favorite word is bumbershoot because it's a funny word and I like bumbershoot. Today we'll learn the fundamentals of speed and energy and how engineers apply these concepts. So by definition, speed describes how fast an object is moving as change in distance over a given period of time. So point A, point B, say that's 50 feet. You cover 50 feet in 2 seconds. And you divide those two numbers, so you get 25 feet per second. Here's an example. When driving a car, speed may be 35 miles per hour on a road, right? This is equivalent to 3,080 feet per minute or 51 feet per second. The numerical value of the speed is the same, but there are many different units we can use to describe it. So usually in science, or scientific problems or notations or examples, etc., we like to use meters per second. Meters is the unit we like for distance, and seconds is the unit we like for time. So by definition of velocity now, moving on, basically it is speed with direction. So say you have a value of 35 miles per hour, as earlier for speed, and you throw in west, north, south, east, directions on a compass, or an angle. So you can be saying, I'm heading 35 miles per hour north, or 35 miles per hour at an angle of 30 degrees, right? Example from earlier, or another example would be a car driving at 35 miles per hour. If we were to consider its velocity, we can say that the car is going 35 miles per hour west. So our first activity, which is marble racing, I'm going to be glossing over it to a degree. Our objective is students will learn about speed and velocity by testing on different surfaces. I stated earlier, we know speed is distance over time. So we get to know d as distance, t as time. So distance over time, distance divided by time equals speed. Here's an example of how we can calculate that. A car travels 120 miles, total distance, in 2 hours, our time. So we can plug that into our equation to get that the car is heading at 60 miles per hour. Here are the materials you're going to need. A timer, 2 to 3 empty paper towel rolls, some masking tape, 1 marble or similar small ball, piece of paper, and a ruler. Step 1 is setting up a table like the right. So you got trial times speed, 5 trials, and leave the speed column empty for now. And for each trial, we're going to be recording a time. Step 2, place your paper towel rolls together with masking tape. This will be your ramp. Now, with the paper towel rolls, or a ramp, we're going to set up a slope 3 finger lengths from the ground. Step 4, place the marble at rest at the top of the surface, then gently release. Record the time for trial 1. Now, apply force on the marble to push the marble down to the surface and time it. Record the time and put it under trial 2. For step 6, adjust the surface to be less steep, around 1 finger from the ground. Example, I guess, or how we would visualize this, say, instead of 50 degrees, it's now 40. And record the time for that, sorry. Step 7, now we want to increase the incline. So instead of 50 degrees, now 60. We want it to be 1 hand from the ground now. And record this for trial number 4. Step 8, place the paper on the surface to try and obstruct the marble from running down the surface and time it again. Record on the trial number 5. Step 9, Measure the length of your surface, the distance the object rolled down the surface. On your paper, set up the equation, speed equals distance over time. We can now calculate the speed for each trial, as we know the distance and we know the time. And distance is constant for all of these. Share what your speeds were. What did you notice? Discuss. What think, actually. Question yourself. What affects speed and how? The incline? How hard you push off? The surface? Any of these variables that we used earlier. 5-minute break. You could take this if you like. Pause the video, go do something else. But for the purpose, I'm just going to be glossing over this. Our next activity, homemade wind turbines. So students will model wind turbines at home to understand how we can use natural forces to create energy. Here are some sources of energy. This is coal. We know what coal is, I'm assuming. You put it in the campfire or you light it and it creates heat. Solar panels use the sun's UV ray to create energy. Wind turbines use wind to spin a propeller blade, which converts to energy. And oil. Energy from oil. In cars, gasoline is extracted from crude oils that are fracked or mined from the ground, or extracted, and is combusted for transportation. Oil is also burned to produce steam or exhaust that turns turbines. Combustion is a high temperature reaction that produces heat, and exothermic reaction produces heat, and carbon dioxide and steam. Heat is related to kinetic energy in the way that how fast the particles are moving is what we measure heat in. So kinetic energy is also how fast, or the energy of movement, essentially. Energy from coal, we use coal to burn heat and water to create steam, which drives turbines to create energy. Energy from the sun, solar panels take in sunlight and convert it from heat to volts of electricity used for things like heating homes, powering air conditioning, turning on the lights, videos, charging, etc. Energy from the wind. We build wind turbines, which have panels that rotate due to the wind, creating electricity. So, here's basically how a wind turbine works. Wind turns the propellers of the turbine, which turn a rotor inside the turbine. The circular object that rotates to create electricity is the rotor. If the wind is stronger, the propeller moves faster and more energy is created. Here are the materials you're going to need. And again, like the other activity, I'm going to be at least slightly glossing over it. You're going to need a toilet paper roll, 3 wooden skewers, 8 to 10 inches long, preferably. Small 3-inch by 3-inch square of cardboard or cardstock if you have it. 2 pieces of paper. 2 plastic pony beads, a single hole punch, scissors, a pencil, glue stick, and hot glue or super glue. Adult supervision recommended, and some tape. So step 1, using the hole puncher, punch 2 holes across each other at the top of the toilet paper roll. So as seen right here. Step 2. Measure 4 3.5-inch length sections with a ruler and mark them. Cut out the marks. If you have difficulty, try cutting as much as you can yourself and snap off the rest. Step 3. On your last skewer, measure out 2.25 inches. Cut out this 2.25-inch segment. Step 4. Mark up the paper into 3x3 squares and cut 4 out. Fold in half, then unfold. Apply glue down the fold. Place the skewers there and stick 2 sides together with glue. Gently curl each of the paper along the skewer axis. So, seen right here. Step 5. Cut out a small circle of cardstock around 1 inch in diameter. Step 6. Use the hot glue stick to glue the 4 longer skewers at 4 points on the circle. 1, 2, 3, 4 on the circle. If hot glue is not available, use super glue to try and attach it. Allow time to dry if necessary. Adult supervision is strongly advised so you don't burn yourself or get super glue on your finger. And takes a while to come off. Step 7. Use hot glue or the super glue to glue the shorter skewer in the center of the circle. As stated earlier, adult supervision recommended. Step 8. Put a pony bead on the center skewer and push it down the entire skewer. Gently insert this protruding skewer into the toilet paper roll through the hole punch at the top. Step 9. Attach the pony bead to the other side of the skewer. If necessary, glue the bead to the skewer so it looks like so. On the right, and keep a little cone and decorate it. This is optional for step 10. Cut out a Pac-Man shape of paper around 4 inches in diameter. Diameter is essentially just draw a line straight down the center or measure from top to bottom of a circle, which is any point. Glue the 2 flat lines together to make a cone and glue the base edges of the cone onto the roof, either with Lego glue or hot glue. So make a cone essentially, and if you want. Step 10. Test your windmill by gently spinning the panels with your hands. They should actually spin. If you want to test it in a natural windy environment, leave it outside on a windy day and observe. Discuss. Why do you think wind turbines aren't very used often in the US? So, they are? It just depends on where you live, essentially. So, if you live in California, or where I'm located, Northern California, and you keep driving to Sacramento past the city of Tracy, there's an area with lots of wind turbines. And this is because this is a very windy area. Wind turbines need an area to be windy, so on top of hills or higher in elevation, or places like the Sahara Desert to be efficient, right? So you can't go willy-nilly placing wind turbines everywhere because 1, they take a bunch of space, 2, they're semi-expensive to put, and 3, as I stated earlier, they're not efficient in some areas. So thank you for coming. We will see you next time. As stated earlier at the start, here is our website, STEMpathize.org, Instagram, STEMpathize.us, and YouTube, STEMpathize.